All right, so I'm going to go through just a couple of problems of each part. Part A probably might go through the whole thing just because it'll go relatively quick. But when we're talking about our chemical reactions unit, we are going to be breaking it up basically into four different parts, as you can kind of see here, where we have our balancing. That's probably the most important part of this, making sure that everything is obeying the law of conservation of mass, and then making sure we can go from name to formulas. Again, just using the states of matter and the elements and ions given and all that fun stuff. Identifying reactions, because we then eventually predict the products of reactions based on what type of reaction it is. So I'll go through a couple of these, and then I'll go through any others during class if you would like me to. So the first one we're going to go through is number one. This is a combustion reaction, or CHOs. The tip and trick here for the CHO reactions was to balance them in that order. So first, I'm going to balance the C's, then I'm going to balance the H's. Lastly, I will balance the O's. The reason I do that is because there's this O here and this O here. They're both on the same side of the reaction. They're on the product side. So in terms of them splitting up, whatever changes I make to those molecules in terms of a coefficient, it's going to change the O in two spots. So that's why we saved that for last. So let's look at the C's first. The C's, I have four C's on the left, so I'm going to put a 4 out here, 4 on the right, because that's going to give me 4 C's here. Now, it doesn't give me 4 C's like that in a subscript form, because that would change what the actual substance is. It just gives me 4 of this combination, so it'd be like 4 CO2s, right? CO2 molecules, so on and so forth. So I put that there. That's also going to change the number of oxygen I have. We'll worry about that in a sec. So here we got hydrogen. There's 10 hydrogen over here. So I'm going to put a 5 here because 5 times 2 give me 10 hydrogen on the opposite side. And now we work on the oxygen. Now oxygen here, 4 times 2, I have 8. 5 times 1, I have 5. 8 plus 5 gives me 13 oxygen. So I have 13 oxygen on the right, which means I need 13 on the left. And notice, each of these molecules for oxygen, since it's a diatomic, comes with a 2. Now, that being the case, there's no way, no easy way at least, I could get a whole number multiplied by 2 to get to 13, right? So what we would have to do is put some type of half out in front, which in this case would be 6.5. Now, knowing that we can't do that, what our fix is since everything happens in a ratio compared to one another, we just have to make sure that we multiply everything by 2 to change it to a whole number. And the reason why we don't just change that is because, again, everything happens in a ratio. So that 1 that we had there goes to a 2, and this goes to an 8, and this goes to a 10. So those top coefficients are actually what those balanced things are. So in this case, how about we skip down to number 3, where now I'm working with some polyatomic ions. And these polyatomic ions, if I see them appear on both sides of the equation, they can be treated like one thing, so that instead of balancing, for this instance, nitrogen and oxygen separately, we can actually balance the nitrate group as a whole, make it easier on ourselves. So as I look through, I notice that I have 1 sodium on the left side and 2 on the right. So my fix for that would be putting 2 sodium on the left. That gives me my 2 sodium. It also gives me 2 of these nitrate groups, as we can see. And the cool part about that is that I have 2 nitrate groups on the right already, since it's attached to a lead that has a positive 2 charge. So that one, actually, we are done. All right, and see how easy it was to treat that nitrate group as a whole instead of looking at the nitrogen and oxygen separate. And sometimes that can get a little bit more confusing. And of course, if there is a blank here, that just represents 1, but it's good practice just to not include the coefficient at all then. If we write it one time, there's at least 1 there, right? It's what we call understood. For number 5, all right, part B, this is where we're going from And I believe it should have, okay, it did fix. This is where we're going to have a written chemical equation. We want to write the correct formulas. So we want to turn it into something that looks like one of those from above. So all we have to do here is pay attention to the substances that we're given. In this case, we are told that this is aqueous, which is a solution, magnesium sulfate. So I look and find magnesium and its charge. Sulfate is a polyatomic and its charge. I notice that my first, if I crisscross those charges, my first substance here is going to be MgSO4, and it's aqueous because it tells me that it's aqueous here. And it reacts with, anytime I see reacts with, that's where I put a plus sign, aqueous sodium hydroxide. So sodium, Na+1, hydroxide. A lot of us on our quiz put just H. That would be hydride. Hydroxide is actually an OH group. On the back, it's a polyatomic, -1, and we see that we have Na and OH. Aqueous, right? Include the states of matter. That is going to be important for our reactions. And then it says that produces, so now that's where my arrow comes in, like I put there. Aqueous sodium, all right, sodium's a +1. Sulfate, we know, is the SO4 -2. So when I have sodium and sulfate, the +1 and the -2, I crisscross the charges. I need 2 sodium to balance out 1 sulfate ion. That goes away. It was aqueous, so I put the AQ there. And then, of course, and means plus. Magnesium, which is the Mg+2, and the hydroxide, which is OH -1, solid. So I have Mg, which is a +2. OH is a -1. I crisscross those charges to get the subscripts, and I end up with needing 2 hydroxide polyatomic ions there. And that was solid. Now my last step, you don't have to draw these lines, but I do just so I have a place to put coefficients, is balance the equation as a whole. I can go in any order because it's not a CHO reaction. Mg, I have 1 on the left, 1 on the right. We're good. For sodium, I have, or sulfate, I'm sorry, let's go in order. Sulfate, I have 1 sulfate group on both sides. That's good. Sodium, I have 2 on the right, so I'm going to put a 2 out in front there to get 2 sodium. That's going to give me 2 hydroxide groups because I have 2 on that side. We are balanced and we are good to go. Identifying following types of reactions. All we have to do is base this off of the reactants, really. And what we were able to do in 06, the types of reactions and notes, we were able to identify what type of reaction should occur strictly based off of those reactants. In this case, when I start with only 1 compound, right, 1 compound at the start, there's going to be a decomposition reaction, which means that it's going to break up into subparts, right? And what we would usually see is it's going to be just a binary compound breaking up into its individual elements. For the next one, we see that we have 2 elements at the start, right? 2 elements at the start means that they are going to combine and make 1. That is what we call synthesis. So synthesis, it synthesizes and combines to form 1 compound in the end. Fe is an element, so I have 1 element here, but I also have 1 compound. If I have an element and a compound, that means that I have a single replacement reaction that's going to take place. That single replacement reaction is going to be the element taking the place of the other element in the compound that's most like it, right? Metals replace metals, non-metals replace non-metals. So in this case, iron replaces silver, and this is a single replacement, SR. For number 10, we have 2 compounds. So if I start off with 2 compounds, then that means that I am going to have a double replacement. And that double replacement is going to have the first elements do a little do-si-do. They switch spots, they switch partners, and anytime that I switch partners, I know that I'm going to create new compounds in the end, and creating new compounds in the end means that I'm going to have to rebalance charges because different things with different charges are going to end up with different partners. All right, then last but not least, of course, here we have one element and one compound as well, but the difference between 9 and 11 is that the element and compound that we are using are all CHO. And if that's the case, this is automatically combustion. And combustion reactions always produce these two products, CO2 and H2O, always. All right, so then we go down here. I'll do an example. Maybe I'll do an example of 15 and let's say 12, because why not? So for 12, I look, it's two compounds, therefore I know that this is a double replacement. What happens in a double replacement? Oh, the first two swap spots. So you can write them in any order. However, at the end, you have to make sure that you have, at least in the compounds that you form, the positive ion, or the metal most likely, come first. Metal always comes first, positive first. Sodium is going to end up with the NO3. Now notice, I do not transfer that 3 over to that side for the sodium. Right? There's only a 3 there because the sodium here is a +1 and the phosphate group is a -3. This 3, however, does go over because it's part of the group. This is an NO3 group, which means that it acts like one thing. That 3 is actually a part of it. It attaches to it. So we cannot get rid of that. So now because I created a new compound, I'm going to rebalance the charges. Each one, +1, -1, I see that I only need one of each there. All right, and then we go plus. Next one that's going to be created was the lithium, taking the place of the sodium with the phosphate group. Now that 4 also travels because the phosphate group, that 4 is a part of it. All right, so that doesn't change. Let's say that this was PO4 2. The PO4 would go over, but this 2 would not. Again, that's just when we have multiple polyatomics, we use the parentheses. So rebalance the charges. Lithium's a +1, phosphate group -3. You crisscross them. I need 3 lithium to balance out 1 phosphate. Now that I have my nice formulas, I can get rid of all of that. And now all I have left to do is balance. So I have 3 sodium on the left, so I'm going to put a 3 in front there. That's going to give me 3 sodium and 3 nitrate groups, which means I need 3 here to get my 3 nitrate groups here. And that's also going to give me 3 lithium, and that'll balance out the 3 lithium that I have on the product side. So 1, 3, 3, 1, based on how I wrote it. If you switch the 2 products in the end, it'd be 1, 3, 1, 3. Does not matter. And what I mean by that really quick is that if you decided to write it like this, right? Either way, it does not matter what order. The only order that matters is I cannot, whoops, still getting used to that. I cannot write this like this, right? Because that means that I'm putting the negative first, and I don't do that, all right? So see if there's an easier way for me to, there we go. Oh, you geez Louise. There we go. Let's not touch that anymore, huh? Well, I'll at least put it back to, every little thing, huh? You'd think. I would figure this out by now, but evidently not. All right, here we go. So I said I would also do 15. So 15, it happens to be 2 elements at the beginning. 2 elements is going to be a synthesis, which means they get together. Please don't fall in the trap of just combining these. First of all, this also is an L. It is not an I. There's no AI element or compound there. ALBR, and some of you are going to want to write 2 because you see the 2 here. Remember, Brinkelhoff or Honkelbrief. Right? All of these are diatomics. That means that when they are by themselves, they have to exist as a pair, just like O2 is, just like Br2 is, right, so on and so forth. However, when they are attached to something else, they do not need the two, right? They only need the two because if they're by themselves, there's nothing else for them to hold on to, right? They are what we call insecure. But now that it's with the aluminum, now this number is going to be based on the charge of what it's attached to. Aluminum's a +3 and the bromine's a -1, so I'm actually going to need 3 of them there. So that is how we identify the correct formula. All right, then we balance, right? 2 and 3 have 6 in common when we're multiplying, so that's what we do when we do coefficients. We multiply, and that's how we can balance out those. What I would say is for these, it's 1, identify the reaction type. Without identifying the reaction type correctly, you won't be able to actually predict the products because you won't know what's supposed to happen. So once you identify it, you're then going to predict what the products would be. So predict the products, and please make sure to rebalance charges. All right, and what I mean by that is when you're making a new compound, you have to rebalance the charges so that you have the right number of subscripts for the formula, right? You have to have the ratio of things that are inside the compound correct before you can then balance the whole equation, right? So that's kind of like the order in which we look at these and tackle these. But this is pretty much Unit 5 in a nutshell. So that should be it. If you have any other questions, then you can always ask me in class or find a time outside. All right. See you later.